In section 6.3, we're going to talk about applications of the normal distribution. And we're going to talk about distributions, normal distributions that aren't just the standard normal distribution like we talked about in 6.2. So remember in 6.2 we talked about the standard normal distribution, which the mean is always 0 and the sigma is 1. And on our calculator we use normal CDF. Now sometimes we'll want to find probabilities for other normal distributions with a different mean and a different sigma. And it could have any mean and any sigma. Okay, so a unique normal distribution is defined for each set of a mean and a standard deviation. But our calculator is not going to have a different function. It would have to have infinitely many buttons, which would just be absurd. But we can actually use the normal CDF. So we want to find the probability of a range of values. So remember, if it's a specific value, if it's something like find the probability that x is exactly 5, it's always the probability 0. So the first thing we're going to do is sketch on a normal distribution our boundaries. Okay, so, maybe we're going everything bigger than 5 or between 3 and 5 or whatever we're doing. Now, for each of the boundary lines, unless it's infinity, we're going to find the z-score. So remember, here's the formula for the z-score of x. We take x minus the mean over the standard deviation. And the z-score, the whole purpose of the z-score is it actually converts everything to a standard normal distribution. So once you have the z-scores, you're going to use normal CDF with the z-scores. Now, if you're doing everything less than a value, you'll still use negative 1,000. You don't have to change that to a z-score. Or if you're doing everything bigger than a number, you can still use 1,000. You won't have to change that bigger to a z-score. Okay, so our first example says, what percent of the adult population has an IQ less than 80? So it says, assume that the IQ mean is 100. So the middle is at 100, and the standard deviation is 15. So 80 would be just less than one standard deviation, or just more than one standard deviation away. So this is 80. We want everything less than 80. So we need to find the z-score for our boundary value, 80. Now, our lower value, we'll still just use negative 1,000. You don't have to find a z-score. So the z-score for 80, we'll take 80 minus the mean of 100 over the standard deviation of 15. And this gives us negative 1.33. So now that we have the z-score for our boundary, we can use the normal CDF on our calculator, and we're going to go from negative 1,000, since we're going, really we want infinity, but like we've talked about, our calculator doesn't have that, up to this z-score of negative 1.33. And when we put that into our calculator, we get 0.0918. So this means the probability that x is less than 80, so if you just randomly chose an adult that they'd have an IQ of less than 100, is 0.0918, which of course is 9.18%. Okay, now the same situation, we're talking about the adult population, okay? And we want to know what's the probability if we choose a person that their IQ is between 90 and 115. So the mean is still 100, and the standard deviation is 15, so we want to go figure out between 90 and 115. So now we have two boundary values, and we'll find the z-scores of both. So the z-score of 90 is going to be 90 minus the mean, which is 100, over the standard deviation, which is 15. And that gives us negative 0.667. And then we find the z-score of the other boundary value, 115. This is 115 minus 100 over 15, which is equal to exactly 1. So now that we have the two z-scores, we use the normal CDF function on our calculator. We go from negative 0.667 up to 1. And this gives us 0.5890. So if we randomly choose an adult person, the probability that their IQ is between 90 and 115 is 0.5890, or about 58.9%. Okay, example number 3 says, assume that the human body temperatures for healthy people are normally distributed with a mean of 98.2 and a standard deviation of 0.62 degrees. So a hospital uses 100.6 as the lowest temperature considered to be a fever. What percent of normal healthy people would be thought to have a fever? Okay, so for some people, their temperatures run a little higher. We want to know what percentage of people are they healthy? Their temperature's just higher, but we would think them to have a fever. So the mean is at 98.2, and our standard deviation is 0.62. And we want to know so this represents the normal people, healthy people, their temperatures. And we want to know what percentage of people is their normal temperature over 100.6. So everything greater than 100.6. So we're going to find the z-score of 100.6. So we'll take 100.6 minus the mean of 98.2 over the standard deviation of 0.62. And that gives us 3.87. So since we're going greater than, we're going to go from that z-score, 3.87, up to 1,000. Okay, and that gives us 0.0005. So the probability of a person who's actually healthy but has a temperature above 100.6 is 0.0005, or really, really small, which is good. We wouldn't want healthy people to be thought to have a fever. So if someone has a temperature of 100.6, you can be pretty sure that they actually have a fever. So of course, this is only 0.05% of people who would be in that situation. Now, just like we did with the clock example in section 6.2, we can work backwards. So we can start with the probability and find the x value that gives that. So again, we use the inverse norm. Now, what we have to be careful about is that this inverse norm actually gives us back a z-score. Then we're going to use the z-score formula to find the x value. Okay, so we want to know what IQ separates the lowest 10% of people with the lowest IQ from the upper 90% of adults. So here, remember the mean is 100 for our IQ problems, and the standard deviation is 15. Now, we want to separate the lowest 10% from the upper 90%. So remember, in the inverse normal distribution function, we put the area to the left. Okay, so the area to the left here is 10% or 0.10. So we're going to put inverse norm 0.10, and we get out negative 1.28. So this is actually the z-score for this x value. This x value that's going to give us this, where this area is 10%. So remember the z-score formula. Z of x is equal to x minus the mean over the standard deviation. So we can plug in three things. The z-score, 1.28, the mean, which is 100, and the standard deviation is 15. So now we do a little bit of algebra to solve for x. So we're going to multiply both sides by 15. So we have 15 times negative 1.28. Which gives us negative 19.2. So that's equal to x minus 100. And then to get x, we would add 100 to both sides. So we get that x is equal to 80.8. So that tells us that the IQ that separates the lowest 10% from the upper 90% of adults is 80.8. So when it's not just the standard normal where the mean 0 and 1, you have to do this little extra step of using the z-score formula to find the x value. So we'll do one more problem like this. So example 5 says that birth weights in the U.S. are normally distributed with a mean of 7.52 pounds and a standard deviation of 1.09 pounds. A hospital wants to set up a special observation area for the lightest 2% of babies. So we want to know what weight should be the cutoff. So we're saying the lightest 2%, we want to know what's the cutoff, what's the X value, where this tail would have 2%. So that's what's to the left, so we're going to do inverse norm of 0.02. When we do inverse norm of 0.02, we get negative 2.05. Remember, this is a z-score again, so we're going to use the z-score formula, which is x minus the mean over the standard deviation, and plug in the z-score, negative 2.05. The mean in this problem was 7.52, and the standard deviation is 1.09. So we multiply both sides by 1.09. So that gives us negative 2.2345. And then we're going to add 7.52 to both sides. So if we round to 2 decimal places, we get x is equal to 5.29. So the weight that should be used for the cutoff for the lightest 2% of babies is 5.29 pounds. Okay, so the main concept of section 6.3 is that if we just have any normal distribution, not the standard normal, the z-scores get involved. So we find the z-scores first before putting it into our calculator. Or if we're using the inverse norm, we get a number out of our calculator, which is a z-score, and then we use that to find x.